Hello and welcome. I want to talk a little bit about sets. Now, sets are just collections of objects. Well, how do we identify collections of objects? How do we write them? How do we describe them? Well, we could just write a list, right? Well, and that's basically what we do when we describe a set in math too. We use this curly bracket. This curly bracket to indicate, hey, I'm going to list a set here. Let's just list the letters A through E, say. I close with a curly bracket. Just listing them. It could be anything, numbers 5, 10, 15, 20, or, people or objects or whatever. A set is just a collection of objects and we're just listing them. Joe, Jack, and Jeanette, say. And we call this roster notation. Roster is just another name for a list, really. So there are other, these are pretty small sets. Sets of 5 here, 4 here, and 3 here. But what if we have larger sets? Maybe we want to list all these numbers, all the counting numbers, 1, 2, 3, 4. Well, I can't list them. There's infinitely many of them. I can't list them. So I'll just put 3 dots here to list them. That's one way to write them. By the way, here we'll call these the natural numbers. There's some debate in the mathematics community that natural numbers should include the number 0 as well. It's really just a convention. If there's ever any confusion, make sure you ask. But here we'll be calling the natural numbers just these positive counting numbers, the non-zero, without 0 in there. And by the way, if you're using that system, this convention, usually if you include 0, you call those the whole numbers. If you start including negative numbers, well, I can start from essentially negative infinity up to, I don't know, negative 3, negative 2, negative 1, 0, 1, 2, 3, dot, dot, dot. And that's negatives, 0, and the positives, positive natural numbers. So we call these the integers. Sometimes the lists we make are more complicated, and so we need to have better ways of writing them. And let me show you that. It's called set builder notation. I'll write that here, set builder notation. And how that looks, it looks like this. I still start the same way with the curly brackets, but I make a little placeholder, and I'll say how I would say this in English as I write it. I'll say this: the set of all numbers x such that, this little vertical bar means such that x is an odd natural number. Now, if we were to list this, we could just list it like this: 1, 3, 5, 7, dot, dot, dot. As soon as it's clear what the pattern is, you can write those dots. And it's arguable that that's just 1, 3, 5, 7, dot, dot, dot is an easier write than this big long x such that x is an odd natural number. But I want to give this simple example because sometimes it can get really complicated, and it's not really that easy to list the numbers. For example, I could write the set of all x such that x is an odd natural number with 3x less than 82? Why not? Well, this might be kind of tricky to write. You'd have to do some little mental arithmetic as you go. Well, I know it's 1 in there because 1 times 3 is less than 82. 3 times 3 is 9, which is okay, so we're good. 5 times 3 is 15. And it would take a while, right? And we would probably end up with 81 because 81 is less than 82, and 81 is the largest multiple of 3 that's less than 82. So we could list it, but listing it doesn't really explain what's going on as well as what's going on up in the set builder notation. So sometimes set builder notation is a lot easier to use. So anyway, that's a little overview of set notation. There's a couple more sets I want to talk about. So I talked about natural numbers, whole numbers, integers, and I want to show you another use for that set builder notation we talked about. The set builder notation really works if we want to describe the rationals. Now, what are the rationals? So I mentioned the natural numbers and whole numbers, which contain the natural numbers because it's just adding 0 there. And then, so let's write those again. So we have 1, 2, 3, 4, etc. That's the naturals. Natural numbers. 0, 1, 2, etc. is the whole numbers. Basically the natural numbers are contained within the whole numbers. Then I gave the negatives. Then I gave negative integers, or the negative numbers, included the negative numbers, which give us the integers. Well, we're just adding some more numbers to our list. That gives us integers. Well, what about fractions? If we want to add fractions into this, then we got a whole new list. And well, I can't list fractions. They're difficult to list. You can do it, but it's kind of time consuming, and there'll be lots of dots, and it's not a nice list. It's not very useful. So instead, we use that set builder notation to describe the rationals. And we describe it as the set of all P over Q, is the fractions, right? Such that P and Q are integers and Q is not equal to 0. Now, why would we do that? Well, that's so that we don't divide by 0. It's just a requirement that we have to stick in there just in case. So these are the rational numbers, or the rationals. Well, once we have that, okay, so those are rationals. So examples of rationals would be 3/5, negative 2/3, and also all the numbers in the previous sections, in the previous sets, which would be like 0 and negative 8. All of those could be considered rationals. So what's next? You think, well, just about every number is a rational number. I mean, could be a rational number. Can you think of any non-rational numbers? Well, it turns out that those ancient Greeks back in the day had a problem. They took a square, one on a 1 inch or 1 foot on a side, and they wanted to say, well, what is the length of that guy? Well, they wanted it to be a rational number really bad, but turns out that it's not. And if you know your Pythagorean theorem, the length of that hypotenuse, the square of that length, is the square of the other two sides, is the sum of the squares of the other two sides. So that's 1 plus 1 is 2. This equals the hypotenuse, C, say, squared. Well, that means that C itself is like the square root of 2. Well, what does that mean? I introduced this new symbol, the square root, which I'm sure you've seen. Well, it turns out that that number cannot be written as a fraction. It does not equal P over Q. And it's fairly simple to prove that, but I'm not going to do that here. But it's pretty well known that you cannot write that as a fraction. So then what is it? Well, if it's not rational, then it's irrational. And that doesn't mean irreasonable, it just means not rational, really. And so irrational numbers include, like I said, square root of 2, square root of 3, basically anything that isn't a perfect square. The square root of it's going to be irrational. Other fancy or well-known constants like pi, e, there's another one called phi, which is the golden ratio. There's lots of them, but you can't list them. There really is no way to list these guys. There's no nice concise way because we've got names for some of these irrationals, but we don't have names for all of them, and there's a lot of them. There's way more irrationals than rationals. If you combine the rationals and the irrationals, if you combine all the fractions and all the numbers that aren't fractions, then you get what we call the real numbers. And these guys, this is basically what you see when you see a number line. You got 0 there, and you got positive real numbers on this side, and negative real numbers on this side. Now, the rationals actually do fill up those number lines pretty good, but actually there are irrational numbers in between those rational numbers. No matter how no matter how close two fractions get, you can find an irrational number in between them. That's how densely packed those irrationals are in the real line. And most of them don't have nice representations like those guys. So anyway, that's an overview of all the number sets that we're going to be working with. Primarily, rationals are really important. How they're represented as fractions or decimals, we'll be working with that. You want to have your skills pretty well refined with those. If you have any questions, let me know. Thanks a lot, and I'll see you next time.